This is Lecture 8C on the calculation of center of mass in 2 dimensions. Now we're going to look at 2-dimensional problems. Before, for the 1-dimensional problem, density was reported as a linear density. So for 1-dimensional problem, rho L is in kilograms per meter. For the 2-dimensional problems, the density is in kilograms per square meter. To find the total mass, we need to multiply by the area. Okay, so right here, the total mass will be this density per unit area, right here, times the area. If the density is constant and the area is easy to calculate, then this is the total mass, then would just be rho A times the area. Okay, let's consider a plate, and we'll put it right here on the x-axis, set it down on the x-axis, and say it is straight. It's flat at the bottom of the plate, and the top is described by some f of x, some function of x. Okay, this is my plate. So I need to calculate the area in here and multiply it by rho A. However, if rho A is not constant, it's going to be a little bit different. The area is going to be the area under the curve. So that is a definite integral from, let's say this is 0 to 10. This would be the integral from 0 to 10 of f of x dx would give me the area under the curve, would be the area of my plate in these dimensions. If anything's more complicated, of course, you can make adjustments easily once you see how to do the problems. If the mass is constant, you would just multiply it by this area. If it's not constant, you must consider that it's the usual thing. I divide the area into little tiny strips, and I would have to take the area of each strip, which would be f of x star times dx, and I'd have to multiply that by the area, say x star is here, in that little strip. Add up all the strips, take the limit as the number of strips goes to infinity, and end up with this definite integral for the total mass. So here's my total mass. I integrate over the region of interest, in this case 0 to 10 in x, rho A of x, which is my density in kilograms per square meter, possibly varying in the x direction, times f of x dx, which gives me the area. You could just as easily have done this in y by making horizontal strips. But this is the calculation that you need to know right here. Okay, so write it again. The total mass is the integral from, I'll just say x1 to x2, of the density in kilograms per square meter, possibly varying in x, times f of x dx, f of x being the curve that defines the upper boundary of the plate. Now when we were looking in 1 dimension, in x dimension, then the center of mass was located at some point, some point x bar. That was my center of mass. Some people go like this. Okay, if I'm looking, this is a 1-dimensional problem. If I'm in a 2-dimensional problem, I'll just make it very regular. The center of mass, put a coordinate system to it, here's my x and y, is some point. It will have 2 coordinates, x bar and y bar. So we need to find the x coordinate for the center of mass and the y coordinate for the center of the mass. So in 2 dimensions, we have 2 calculations that we have to do. Right. To do this, when we did the one in 1 dimension, we had in our coordinate system, of course, a 1-dimensional coordinate system, we had the point x equals 0, and we considered the moment about x equals 0. Remember, x bar was a moment about x equals 0 over the total mass. We're going to have a similar calculation here for x bar and y bar, but instead of using x equals 0, because we're in 2 dimensions, we're going to look for the moment about the y-axis and the moment about the x-axis. As I've written here, there are 2 plans for calculating these moments. One, you can divide the plate into vertical strips, which is what we're going to do, or you could divide the the plate into horizontal strips. We're using, again, very simple strips, and you can extend this later in physics as needed. What we're going to use here are the vertical strips. So what we've done is we're going to put on here a plate, and we're going to say the plate has some upper boundary, which is given as some function of x. Other than that, the plate sits perfectly fine right on the x-axis. Just do a problem like this. Okay. Now, what I'm looking for is the moment about the y-axis. Right. This is similar to the one-dimensional problem when I was looking for the moment about x equals 0. It's similar to the moment about the y. The y down here means the y-axis. Right. So what I've done is the usual, dividing it up into little strips. In each strip, I calculate the mass in this strip. So the mass is the density in the strip times the height of the strip times the width of the strip, which is delta x in my crude approximation. That's my mass. And now to get the moment, I need the distance from here to the y-axis. Well, if this is my x star, the distance to the y-axis is just x star. So in my crude approximation, for the moment in the nth strip is going to be x star, which is some average value in that strip, x star, times the density times f at x star times delta x. To find the total moment, I sum over all the little moments. Then I take the limit as the number of strips goes to infinity, and I get this definite integral. The moment about y is a definite integral, whatever these limits are. Let's say this is x1 and x2, so I have to go from x1 to x2 of x, previously my x star, but I've taken the limit here, rho a of x, that's my density in kilograms per square meter, times f of x, which defines the upper boundary, dx. This is the moment in y. X bar, this is the x coordinate system of the center of mass of the two-dimensional objects, is the moment about the y-axis divided by the total mass. Now, to calculate the y component of the center of the mass, we use a little bit of algebra. What we're looking for here is the moment about the x-axis, which is the moment about y equals 0, which we write as the moment about the x-axis. So we need the mass times the distance to the x-axis. We're going to use vertical strips, and we'll continue to use them because of the geometry of our problem. So we know that the mass is density times area, which is density times height times width. So it's rho a, that's mass in kilograms per square meter, times the function that defines the upper boundary of the flat plate, times dx, or delta x. What is the distance to the x-axis? We can just find this by taking the average height of the strip. So the distance to the x-axis is half of x to the n, because we're going to look at a point right in the middle of it. Again, we're taking averages, so that gives us half of the height of the strip. So if here's the flat plate here, this is f of x, then we're going to take this point, which is f over 2, as the average distance that this strip to the x-axis. Of course, some are at x, some are at 0, and so when you take the average, it's f over 2. We're going to substitute this into our calculation. Okay, remember that moment is x times mass, distance times mass. Well, in this case, because we're talking about x, it is the distance to the y-axis times the mass. All right. here's the mass, right here. It's a start on it. That's the density times f of x, and then we have, and here's our dx. That will give us the total mass. The distance to the x-axis is half f of x. That's right here. Combining all these, we get the moment in the nth vertical strip about the x-axis is 1/2 times the density in kilograms per square meter times f squared of x, f of x squared, that's the height, that's the function that defines the upper boundary of the plate. Here's your f of x right here, dx, or rather delta x. Take the limit, we get the integral from x1 to x2 of 1/2 rho a of x, f squared dx. Now the y-coordinate of the center of the mass is the moment about the x-axis divided by the total mass. One result that helps simplify calculations is that if the plate has an axis of symmetry, okay, so if it has a vertical axis of symmetry, then the x-coordinate of the center of the mass will lie on that line of symmetry. Similarly, if the plate has a horizontal axis of symmetry, then the y-coordinate will lie on that horizontal line, the y-coordinate of the center of mass. So for example, if you have a circle, so here's a circle, it has, okay, we'll just put it, here's x and y, okay, and here's my circle. It has a vertical axis of symmetry, so the x-coordinate of the center of mass is located on that vertical axis of symmetry. It also has a horizontal axis of symmetry. The y-coordinate of the center of mass is located on that axis. The center of symmetry, or rather the center of mass, is x bar y bar, which actually is the center of the circle, because that is where the vertical and horizontal axes lie.